Welcome everybody to part 3 of the introduction to Clojure thing we're talking about here. Just to recap a little bit, it was a while ago we did the earlier talks, so we have gone through some fundamentals about the data structures, literals and stuff like that you can be using inside Clojure. We talked briefly about interoping with Java, calling methods and declaring interfaces on Java classes and that sort of thing. And we talked also about the different collection types that Clojure offers and how you could sort of associate new values into maps and replace keys in maps and that sort of thing. And that's kind of where we left off last time. So I thought today we'll start with talking a little bit about transformations, which is pretty much how you would break down problems in a functional programming language, is that you would take some input data and you would transform it to produce new data structures. So we will talk a little bit about what kind of transformations you can, how to do those kind of data transformations. So this will still be kind of a fundamental thing, but hopefully it will give some background that you can use to understand further things a little bit better as well. So I've started a new namespace here in IntelliJ, and what I want to talk about today is functions and higher order functions, which is functions that take functions as arguments. So functions inside Clojure are values just like any other value. It's the same sort of type of class of thing as a string or an object in an object-oriented language, or an integer, and that means that you can have functions and you can give functions as arguments to another function, and you can also have a function that returns a function, right? And this is used to great effect to perform data transformations. So just to give an example, I will write here a function that I'm going to call transform random name. And this function will take a transform function as its argument, and it will do something. And I'm going to leverage some of the stuff that we used that we did earlier in the fundamentals part. And in the fundamentals part, we loaded a list of words. So there's actually something in fundamentals called words, I think. Let's switch to that namespace and see. Okay, it's not called words. It's called names. Sorry about that. And this is going to be a huge list of names, so I'm just gonna limit the output and just take 10 of those names. There we go. It's basically a bunch of names. So we have this list of names, and what I want to do is write a function that just takes one of those names at random and transforms it using the function I supply to this function. And to do that, I would call my transform function and give it as the argument rand_nth, which will pick a random element from the fundamentals names collection. So just defining that, and if I execute that over here and give it, oh, I misspelled that, sorry about that. I can give it a function that it should transform something with. And one of the functions that already exists in Clojure everywhere is the identity function. And the identity function just takes its argument and returns it, so it doesn't do anything. And just to demonstrate that this will pick a random name, I got a very interesting name there, Marnix, Herbert, and I can't really pronounce that, but that's fine. So it already picks a random name and it applies the transform function to that random name. But that means I can also replace this transform function with something else. So for example, I can do string uppercase, and it will pick a random name and transform it using that function. We also did another function when we did the fundamentals part that mangled something, right? So we did fundamentals mangle, which just sort of inserts some dashes and reverses the word to encrypt the word. But as you can see, this function is callable with another function as its argument. An example of a function that would return a function is a bit trickier, but what we can do is we can define a typical example in these kind of cases is that you would make an adder, which is a really sort of simple thing. I'm going to create a function that creates an adder. An adder is simply a function that takes a number and adds something to it. And this function is going to return a new function. And you remember we do this, fn, and then an argument list, and then something to do, I guess, add them together. Maybe I should do a line break here to make it a little bit easier to see what's going on. So as you can see, I'm defining a function, makeAdder, that takes a single argument, x, and returns a function that takes a single argument, y, which, when evaluated, adds those two values. And if I define that, I can call it, and I can make an adder that adds 1 to something, and maybe I'll define that as increase, and I can define another decrease function that adds -1 to something. So these are now two functions which I will be able to call. Increase 2 gives 3, and decrease 4 also gives 3. So the interesting thing about returning a function is that the function that you return has access to all the up values that are available in that scope. And in this case, the argument you give here sort of gets baked into the return function. So it's almost like you would have a class adder that would take x in the constructor and then use that x value inside a method that it would call it. So you can solve the same kind of problems that you would be able to solve in Java, for example, by having a class and having some methods and having sort of private members of that method. You can do that sort of thing here as well by just having a let statement or evaluating something outside here and then returning a function that sort of encapsulates those values and makes use of them later. And this is a very, very common thing to do. It's important to realize that this doesn't actually compile a new function. It basically instantiates a new function with a new set of up values. So it's not actually it doesn't have to interpret the code because you do this. It just sort of makes a template for a function that you can sort of slot in different up values into, and that gets returned. So Clojure ships with a lot of these kind of higher order functions that take functions, and you use them for data transformation a lot of the time. And we already saw this is not really a higher order function, but it's a function that transforms input. You saw me call take and give a number and then the names list, right? And this will take the first 5 elements in that collection and return a new sequence that contains those first 5 elements. Conversely, there's drop, which will drop the first 5 elements of the names. So yeah, that gives me a huge list of names, but just skips the first 5, right? So that lets you limit the number of items in a sequence. And the thing that gets returned here is not actually an array. The thing that gets returned is a lazy list or a lazy sequence. And what that means is that we don't evaluate this list at all until I do something with it. It's the list of names here. It's only evaluated because I've printed it. So if I were to sort of stash this list away somewhere, just sort of like put it in a def or something, that wouldn't actually do anything to the elements of the list. So it's perfectly safe to create infinite lists, and as long as you don't evaluate the entire list itself, you can evaluate a bit of it, but you don't. As long as you limit the amount you evaluate, it's fine. So there's a very simple function that is called iterate, which takes a function. We can take the increase function we defined earlier and a start value. And it will take this start value, run it through the function you provide. I'm just going to scroll this a little bit. Take the 0, run it through increase, output an element, output that as an element in an infinite sequence, then take the last result, and run it again through iterate. So this will effectively increase from 0 to infinity, or rather it won't stop ever or at least until the memory runs out. So what I'm going to do is I'm going to take just the first 10 elements from this, and you can see that it runs through that, and it only consumes as much as it needed to consume to be able to finish the job. And effectively what this means, that if I put a print inside this increase function, you can see that, let's see, oh, sorry about that. Oh, you know what? I need to put it inside the make adder function, actually, because it's here we're doing the evaluation, right? Let's just print x. Yeah, let's print x, y, and a plus between them so we can see what's going on. Print line is probably better for that as well. So I'm going to redefine the make adder. I'm going to what? Oh. We're going to redefine the increase function. And if I now run this again, I'm just going to clear this because it's a bit messy. You can see that it runs that function a bunch of times and then sort of outputs the list, but it only runs as far as it needs to be able to complete the job, right? And this is true for nearly all of these data transformation functions in Clojure. They consume a sequence and they return a lazy sequence. So it's only consuming as much as it needs to do to make the work done. So we looked at take and we look at drop, and we're going to be using these a little bit. And we also saw iterate, which is the first sort of higher order function that we looked at. The function that takes a function and calls that function repeatedly. Some other common ones that are very often used is filter, which takes a predicate, and a predicate is a fancy word for a function that takes a value and returns either true or false. So it's a test function. Filter takes a test function, which takes an element, right? We're going to filter over these names again. So I'm just going to filter over the names, and I'm going to scroll up because that's probably helpful. And this function that I give to filter will take a name, and it will decide whether or not to include that name in the returned sequence. So what I wanted to do here is I wanted to call string I'm going to only return the names that ends with the letter X. That can't be that many, right? And here we go. So that's the complete set of names and there's our favorite Marnix again. And I get a filtered list of all the stuff that complies with that filter function. Another very common function to use is map, which again takes a function and for each element I'm going to map over the names again, and here we can transform the value. This will return a list that applies a transformation function to all the elements and returns a list that contains all the transformed elements. So if I were to transform this using string uppercase as above, I transform the name with uppercase, I get a list of all the uppercase names. Now map actually is able to take multiple sequences, and this is not really going to be a good example, but I'm going to give it a range as well of a range that has range returns basically a sequence of numbers up to a maximum value. So it returns all the numbers from 0 up to the value you give it. You can also say I want all the stuff between 2 and 6, and it does that. So that's also a lazy sequence. And what I wanted to do here is return a lazy sequence that contains the same number of elements, all the integers between 0 and the number of names in the names list. And here I give that as a second list argument to the map function. And that means that I can put in index, name index, as a second argument to my function here. And I guess I could just, I don't know, I'll concatenate the index at the end in my transform function, and you will see that it will just keep going like that. And you can put any number of sequences in here and just sort of increase the number of arguments to map and give you something like that. There's also a function called keep, which kind of does the work of both filter and map in one go. So it can sort of help you a little bit to sort of decrease the number of calls you do. And if I give that to what it does is it returns a list of all the elements transformed, just like map did. But if I return a nil from this function, it excludes that element. So I guess in this case, I want to sort of combine these two. So do a when the string ends with x, right? When the string ends with x, I transform it using the uppercase function. And probably scroll a bit. So here we say, all the names, when it ends with x, I transform it to the uppercase. And otherwise it returns nil, so it gets excluded from the returned list. So that's keep. There's a converse function called sum, which does the same thing. I just take the exact same thing that I give to keep here. And so it does the exact same thing, but it only returns the first element that matches. So it returns the first non-nil element, and that was returned from the function. So sum and keep are sort of mirrored in that keep keeps all the stuff that you return, and sum just stops at the first element. So once it finds an element, remember everything is lazy, it won't do any more processing. So you just sort of go through the list as far as it needs to go to find something that matches this result, and then stops. So that's a couple of those. There's also mapcat, which I kind of hesitate to include here, but we'll talk about it anyway because it's useful. So you remember map just goes over all the elements in the list and returns the same size of list, right? Every time if your input list had 10 elements, you get an output list of 10 elements, right? Keep was able to take a longer list and sort of filter out some stuff, so you get a shorter list back. Mapcat allows you to output a longer list as well as a shorter list from a sequence of elements. And it does this by effectively doing about the same thing as keep does, but the idea is that the thing you return at the end of your transformation function is itself a sequence. So if you don't want to return anything, you can return an empty sequence or nil, that's fine too. But if you wanted to return a single value, you return a list with a single value in it. And if you wanted to return multiple values, you return multiple values in that list. So in this case, I can grab the uppercase and the lowercase. Maybe that's a very contrived example, but this will produce a list that has the double size of the input list, because it just sort of runs this transform function. And remember, the logic here can sort of decide to produce multiple values for one element. It can produce 3 values for one element, none from another, and so it can be used in the same way that keep can be used to sort of filter out stuff. This can also filter out stuff from the list and then produce kind of complex transformation. The name mapcat is a combination of the function map, which maps over elements, and concatenate, or concat, which concatenates the results. It sort of maps over everything and then concatenates everything. Effectively, the definition of mapcat is basically running map and then flattening the list. So it flattening all those, concatenating everything together. All of these return lazy sequences back, and the first function we're going to look at here that doesn't return a lazy sequence is called group by, which is very useful in some cases. What it does is it takes the same thing. It takes an element from the list in its function, and it then groups the elements in the list by the return value from this function. So in this case, I want to have a list that, or a collection that is grouped by the first letter in each name. So I get an alphabetized grouping of names. I can use the substring function, and I'm going to use substring of name, and I want from 0 index to first index. So that gives me just the first letter in that string, right? And here we go. So just look at this. There's a couple of names here, but what this returns is it returns a map of. Let's just clean that and do it again. I can scroll to the top. Oh, there's a lot of names. It returns a map, right? A map of first letter to a vector of all the names that starts with T. And the order here is, it's just a hash map, so the order appears in a different order than you might expect. But then you could just sort this collection to get a sorted result back. And I mean, you know, because it's so easy, why not do that? There's a sort by, and since this is a map is in itself a sequence and can be treated as such. So I want to sort them by key, right? The key is this bit here, and then the list here. So I sort my grouping by key, and I get back something that's actually ordered. So you can see like this. So, but it's no longer a map at this point, right? Because the elements are now a list, or rather they are an array, because it's a sort by, or all the sort functions return an array all the time. So it's not. I can no longer look up the names in this, but at least I have it as an ordered thing. if I wanted to be able to look up, still be able to use a lookup, there's actually a different kind of map that's called sorted map instead of hash map. So what I can do is I can take that collection I already have and I can say into sorted map. So you just sort of take that whole sequence and push it into a sorted map. And this gives me the best of both worlds. I have a sorted lookup, but I can also still look up the keys inside this collection. So that's a bit of an aside, but it's very useful to be able to do these kind of transformations. And as you can see, they compose. I can just sort of pipe them into each other, sort of nest them like this. And because everything is lazy, nothing actually produces, it doesn't allocate a chunk of memory and sort of realize that collection. It just sort of like throws away as it goes along, and it's only when I print it or actually turn it into I actually realize it into a data structure like an array or a sorted map. It actually takes up that memory that is used by the collection itself. We also need to look at another fundamental function called reduce, which is one of the more difficult ones to understand, but it's also one of the most powerful ones. So to try to explain this, what it does, it takes a function just like all the other stuff that we've seen so far, and it takes a collection like all the other stuff that we've seen so far. I'm just going to take 1, 2, 3 here to demonstrate. And the function differs from the other ones. You remember the function in all the stuff that we looked at previously just takes a single argument like this. And reduce takes 2 arguments. It takes an accumulator and an element. So accumulate and element. And what it does is that it goes over the collection that you give it and runs this function for each element, with the element argument being one of the elements in the list, and the accumulation argument is the result of the last call to reduce. So this function must return a value, and then the next iteration will take that value as the first argument to this function itself and the next element. So that is kind of hard to think about what that actually means, but just to give you a simple example of what this does, let me just rename these functions, or rather let me rename these arguments to be a bit more clear. So every element will be a number, so let's call that n. Remember, this argument will be 1, 2, 3. And let's call this argument sum. And if I just, in this function, I add the sum to, I add the element to the sum, this will produce the result of adding all the elements in the list. And the way it works is that the first time you run it, it just sort of like, it starts off as, actually there's a bit of a tricky thing here, that reduce actually does something sort of magical if you don't specify an initialization value. So that's the tricky bit, that if you don't actually tell it where to start, it sort of has some internals that works out what needs to happen. And effectively it does, I think the rule is like, if the list has only a single element, it just returns that single element without running it through the accumulation function. So that's the starting point. And then the next iteration will be that, which was 1, in this place, and 2 in this place. And then it will add 1 and 2 together. That value is returned. And the next time the function is run, it will have the result. That means 3 here. And it will have 3 as the element from the list again. So it will sum those together. And the interesting thing about reduce is that all the other stuff that we looked at prior to looking at reduce can actually be implemented in reduce. We can implement all of these functions using nothing but reduce. Now, what if you don't have? What if you need to define this a little bit better? What actually happens? Then you can provide an optional initialization argument to this, which will be the first argument to sum through the first iteration. And in this case, there's no difference because we started with 0 and then we've gone over these, right, and iterated over that. But I can say that, okay, I actually had 10 from the start, and I will add these additional things on top of 10. And I would say that most of the time that you're using reduce, you are providing an initialization value, because if nothing else, for clarity, it really helps to sort of think about what do we start with, because I mean, in this case, it sort of works that it could take the first element and use that, but it's sort of a little bit, you know, it feels a bit weird. But it's also really important to be able to provide this argument, but because what if, like if you started with 0 here, that works with summing the numbers, right? You can sum everything up, you start with 0 and you sum it up. But what if we wanted to multiply everything? If I start with 0, I get nothing back, right? So in that case, the sort of identity value for multiplication is 1, it's not 0. So I need to change the input value like that to have a different starting point. So if I want to do like a power of 2 thing, I can just do a couple of 2's like that, and I can multiply them together. And there's actually a converse function called reductions that lets you see all the intermediate steps. So you just replace reduce with reductions there and just reindent. You can see that I get all the intermediate values that was produced by sort of successively applying reduce to elements in this sequence. So if I wanted to implement filter, for example, using reduce, how would I go about doing that? And this is where we get into like how can I solve problems a little bit in a functional manner. But bear with me, I will try to make this as clear as possible. Let's make our own filter function. And you remember the filter function takes a test function, or a predicate if you want to call it that, and a collection. And I said that I will do this using reduce, so I will try. Reduce takes a function that takes the result of the previous iteration and an element, right? So reduce takes that. It also takes, I can give it a starting thing. And there's a really helpful function called empty, which takes a collection and returns an empty instance of that collection. So just to demonstrate here, I can do empty. If I do an empty map, I get a map back. Even if it has stuff in it, I get an empty map. And just conversely, if I have a vector, I get an empty vector back, even if it has stuff in it. So our filter function will start with an empty version of the collection that we give it. And it will then take the collection to iterate over all the elements in the collection. And how do we make a function that performs the filtering operation? Well, first of all, we need to test. We need to run the test function to determine if the element should be included or not, right? And we do an if statement, and we run the test function that we supplied on the element that we were given. And here we go. We have two paths to go here. Either we include the element or we don't include the element. Now, if we don't include the element, what do? We don't need to do anything, right? We just return the previous result, because it's the same. At that point, it will have the previous collection. From the start, it will be an empty collection, so we don't do anything. Then if it had stuff in it, it would be that collection, right? So if it doesn't have anything in it, we return the result. If it doesn't pass the test, we don't return the result. And the only thing that remains here is like, what do we do if it does pass the test? And what we can do if we have a collection, there's a function called conj, which takes a collection and a value, and it inserts that value into that collection. So if I had A, it inserts B at the end there. So what we need to do in the case that we pass the test function, we need to conj onto our result. We conj the element. Right. So we start with an empty collection. It starts here with the empty collection first time around, and the first time around this will have the first element from the collection. It gives that to the test function. If that returns true, we append that element to the result from the previous pass. If it returns false, we return the previous result without modification. And just to demonstrate that this actually works, let's see, I'm just going to take the same thing here that we had for the filter. I'm going to run that here with our filter. And it works. Same result. Now, it's not actually the same result because our version doesn't produce a lazy list. Our version produces an actual vector. So that's a difference, but you know, I wanted to sort of keep a little bit of complications out of this. I think that it's fairly easy to convert this into something that returns a lazy sequence. Actually, I think it's just like this, maybe. But I'm not sure that this will actually return a lazy sequence, so this might not be. No, that's probably not right. I'm just going to ignore that for now. But we did implement filter in terms of reduce, showing that reduce is a really powerful construct. Now, we can actually do map as well, just as an example here. If we wanted to implement our map, remember map takes a transform function and a collection. And you will see that this becomes pretty much the same thing. We do a reduce, and the reduce function will take the result and an element, right? The same thing here. We start with an empty collection, and we will iterate over the entire collection. So you can see the bones of this are very similar to the filter variant here. The only thing that really differs is what's inside this reducing function. So what do we do here with map? Well, we already know how we add something to a collection, right? We do this using conj. We conged the element to the result. If I did this, it would produce the same input as the output. We just make a copy of that list, right? So the only thing we really need to do is apply the transform function to the element before we add it to the list. So that is map. And let's do our map. And do an uppercase of the name. And it works. Let's do one more, just for fun. We're going to do sum from above. You remember sum takes a test function, just like filter does, and a collection. And we are going to be doing reduce over that. Now here's interesting, right? Because all the time here we're saying like, okay, I'm going to return a list of something. So what do we do here? Result and element. Well, from the start, what is the start value for this? So we can't start with an empty collection because we don't want to return a collection. I guess we'd just start like, what would happen if nothing matches? If nothing matches an element, we would get nil back, right? That's the sort of fallback if nothing works. We'll have nil as the result. And this will perform pretty much the same thing as filter, which had we did like if test fn on the element, and we do something if that's true. Otherwise we do, oh, what happened? Got a terminal for some reason. Okay, so we look at that. Let's just look at our filter side by side here. We can sort of scroll this out of view. And let's see. So we have the filter function and sum. As you can see, that it has the same bones. But what do we do here? If the test passes, we just want to return the element, right? Right? And if the test doesn't pass, we can return the old result. Right? So this will actually do sum. And just to demonstrate, oh, I actually redefined sum. That's probably not very good, because I'm not sure that that's going to work very well in the future. All right, we'll find out. But our implementation of sum should work. Let's see, we did that sum over here somewhere. There we go. If I take this one that we used earlier and use our sum instead. So it should return the first name that ends with X and uppercase it. Ah, I did something wrong, didn't I? I didn't actually implement sum because this is not a test function in sum, it's a transform function. And it should transform the value, and then it should test if it was nil or not, right? So we do like transformed element is transform function of element if nil element, same result, otherwise the transformed element. So what we actually implemented there was sort of like just a find thing that found an element, doesn't actually transform it. I guess that's useful as well somehow, but here we go. And it doesn't work at all. Oh, sorry, nil transformed element, of course. If it's nil, return the result, otherwise we return the transformed element. There we go. Now it works. As you can see, I'm making all sorts of mistakes, and just having this REPL here to be able to try things out really helps to trap those bugs. Now this does the work of sum, but it does it in kind of an inefficient way, because this will actually iterate over each and every element in this collection, right? And really what we wanted to do is, like, once it finds a non-nil element from the transform function, we actually wanted to sort of stop there and don't process anything any further. And what you can do there is there's a special sort of tagging function you can apply to the result called reduced. And if you pipe something through reduced, I previously just returned the transformed element, but now I'm returning the transformed element reduced. And that tells reduce that he can stop iterating. It doesn't have to go any further. And as you can see, it sort of actually changed the behavior of the function now, because the previous implementation would return the last matching element, because it would sort of go, it wouldn't stop at the first element, it would sort of consume additional ones, and it would replace it as it was going along. But this one actually stops at the first element. So this is a proper implementation of sum, I guess. So as you can see, you can use reduce to implement very complex things, and you can implement most functions in terms of reduce. So it's like this really powerful fundamental thing, and being able to understand how reduce works, you can do all sorts of things. I'm not going to try to implement group by using reduce here, but it's absolutely possible to do so. It's just a little bit more tricky. Now, if you look at all the stuff that I've done here, it's a bit wordy, it's a bit messy, because I'm sort of like, I'm having these functions that really don't do a lot, sort of being inlined. Like for example here in the, I did the reductions thing here. Let's look at that again. And I'm just going to change that to reduce, and I'm going to start with 0 and sum them 1, 2, 3. Now you remember this, that this would sum the elements in the list like this. But the thing about functions inside Clojure is that everything is a function from the start that is in the standard library, unless it's a macro. And plus, this thing here, it's actually a function named plus. So it returns it as this is what a function looks like if you evaluate it. But as you remember, you're able to add several things like this, but it's just a function call, which means that whenever you see this kind of pattern, that you're having defined a function and then you're giving it the exact same arguments in the exact same order to another function, you don't really have to do this. You can just take this plus here and replace the entire function with just plus. Because plus is itself a function, and it would take the same arguments in the same order. So reduce plus actually sums something. And you don't even need the initialization argument for this. You can just do this to sum a list, right? And conversely, you can do like, I want to multiply them together. Or I wanted to have a starting point, right? So it gets a lot shorter if you actually start to inline the functions instead of always sort of wrapping something into a local anonymous function. You can just inline the function itself here and save a lot of space. And another thing that's really common to use is that you remember up here we did the adder. Or rather, we make an adder that increases something, and I'm just gonna do something next to this so we can look at it. But this has sort of the same feel to it, doesn't it? You have a function that takes something and then just does a little bit of work. What you can do is that you can instead actually define increase using partial function application. So increase would be partial plus 1. Now partial, what it does is that it takes a function, in this case plus, and a list of arguments, and gives you back a new function that has all those arguments sort of prepended to the argument list. So in this case, plus is a function that takes, well, it takes a random number, or it takes a number of arguments, and it adds them together. And what I'm doing here is that I'm defining a new function called increase, which is equivalent to this. Increase y plus 1 y. So you can see I have the same list here, plus 1 and plus 1 here. And I get back a function that does the same thing. It just sort of, it's partially applied. It has some of the arguments pre-populated. Conversely, you can do a decrease, of course. You can do -1. No, you can't do it actually. You have to add -1 because the argument order to subtract is different, right? It doesn't commute the same way. And this is a very powerful feature when you are using map and filter and stuff like that. I mean, if you look at this call to filter here, we can actually sort of, no, that's not really a good example. But if we had this simple map call here that just takes something and converts it into uppercase, there's no reason for me to wrap this in string uppercase. I can just give it string uppercase directly as an argument, right? It looks the same way. And what you can do is that if you have a filter and I wanted to maybe just find the first element in a list that equals something, you could do like if name is equals to, I guess Winston is a good example as any. I want a list that only contains Winston. It doesn't matter which order these arguments are, right? I can just equals Winston on one side or the other. But this also means that I can instead write this as a partial function application, which means I can have partial equals Winston. And it does the same thing. Because partial returns a function that takes any number of arguments, which is one of the names in this list. The function has Winston as its first argument, always. And there's actually a third way of writing this, which is a bit shorter as well. Like if I were to write filter, what I want to do is I want to do the same thing. I can write that like this and put a little %, which will act as the argument. So in this case, I would say, you see there's a little hash tag here. This is equivalent to this here. Function name equals Winston name is equivalent to hash equals Winston name. And if your function takes more arguments, you can do it like this. 1, 2, 3. You have to give them numbers if you have more than one argument. But this gives us the power to actually place this % anywhere, right? We can put it in here. It doesn't have to come at the end, which means that it can actually work with something like it can work with something like this. I want all the names that end with X. And of course here the name needs to go here, like in the first argument rather than the last argument. But if I put the % there, that also works. So this is useful. A lot of times you're doing one-liners like this, you use this shortened version. If you need to do something a bit more complicated and express something that's a bit more involved, you tend to split it up like this because it becomes a little bit clearer, because you can have like this is not really suitable for use in any other case where it's a longer sequence, right? And just to sort of show you a little bit like a real world example kind of thing, I'm just gonna sort of try to duplicate a function called that we're using to sort of filter. We have this fuzzy filtering, or like type to filter lists. Just to sort of try to replicate that a little bit here. So let's call that function filter options, which will take arguments. It will take a function that transforms an option to a to a text that can be displayed or filtered. And it will take a collection of options, and it will take a filter text. And the idea is that this will return a list of filtered options. It will sort of transform this list of options into a filtered list of options that will be sorted by the score. And what we need to do is essentially we need to treat the case of the list being empty as a special case. So I'm just going to do that. If the list is empty, question mark. So this is not the empty function that returns an empty list. It's the function that produces a true or false value depending of if something is empty. If the filter is empty, if the filter text that the user provides is empty, we want to return the options as is. We don't filter anything, right? But if they do provide a filter, we will map. Actually, let's do this in the inside-out fashion, because I will decorate this as we go along. It will be clear that way. We're going to use the keep functions to do both filtering and decorating in one go. And it will take an option, right? And as the collection it will iterate over is the list of options. And for each of these options, it will try to score that option somehow. And we can use the when sum, which is a sort of a combination of let and when. And it needs to score. It should score an element somehow, or score an option somehow. What I'm going to do is I'm going to just make a really simple scoring function here that just scores something based on the index of a substring inside a string. So like if the string that you type is earlier in the text, that's a better match. So we're going to call string index of, and we're going to need the text from the option. So we're going to transform the option using the option to text function. And we are going to find the filter text that the user types, and that will sort of determine the score. And string index of actually returns nil if there's no match, because we don't, I mean, that otherwise if we return -1, it would be wrong, right? Because it would always score non-matches better than actual matches. But we actually, since it returns nil, we can sort of check for that with when sum, and this will only get executed if it actually returns a non-nil value. Otherwise, it won't do anything. And what we're going to do is return a sort of decorated value. We return the option itself and the score. Right? So that gives us a collection of all the matches from above. We're going to take that result of that function, and we are going to sort by score. And this works because score is a keyword, and if you remember from earlier, a keyword is a function itself, so it can be applied to a map and extract the value for that key. So we can sort this by score, and it will give us a better score for stuff where the string matches earlier in the string, because it's a lower value and it will sort better that way. So, but remember, the contract of this function is that we actually want to return the option itself. We don't want to return the decorated value. We want to return the options in an ordered fashion, but depending on the score. So the final thing we need to do is wrap this again in map, and we extract the option from that map that we just got from the score. So that is essentially what we do when we're filtering, right? We are filtering the list, we're sorting it, and giving you back by removing the decoration of a value. Now, as you can see, this gets a bit, sort of pushes the indentation to the far side here. And to sort of help with that, there's a helpful macro that looks like this. So there's a sort of a little arrow thing here. And what this does, it sort of threads a computation through an expression, which lets us write this in a way where you don't have to nest everything and give like the last argument to sort of become a bigger and bigger sort of expression with parentheses. Instead, we can say like, oh, I want the options, and I'm going to give that to the keep function and sort of provide at every step of the way from the previous result is going to take that as an implicit argument to the keep function. You remember we take keep and give it all the options here. So what I can do is I can remove the option and instead provide that as an implicit argument to keep, like that. And I don't have to nest everything as far. I can do the same thing here. I have the result of this expression is now a list of filtered options with decorated by score and stuff. And I can continue threading that expression to sort by. So sorts by score, and I can then finally extract the options by mapping over that collection and getting the options back. So that's equivalent. It's the same thing that you saw earlier, but it sort of instead reads a bit clearer because it sort of threads this expression here, the options, and then sort by and map. And if I were to sort of break this function out into a separate function, it could be even more clear. I can make a separate function to called score, or decorate with score, I guess. That takes an option, and it probably takes a filter text as well. I can use that code, actually this code, filter text option, decorate with score, keep, partial, decorate with score, filter text. Oh, it actually needs option to text as well, doesn't it? So it might not be a very super good way of doing this, but you could break it up like this. And this gets a bit hairy right now. I'm not entirely sure that everyone is sort of understand what just happened there, but what I did was sort of break out some functionality that I used to have in a local function declared inside there. I broke it out into a separate function that takes all the arguments that it needs, and just making sure that the actual thing that I want to iterate over is the last argument. So the option from the list is the last argument that I will visit, right? And I can then use partial to combine, sort of prepare a variant of this function that has the filter text and the two dependency arguments partially applied. And what I get from that is I get a more clean sort of threading of operations. I can sort of like take this collection and thread it through this and sort of like get a fairly clear sort of like what path does this transformation take, right? And sort of express it in a little bit of a cleaner way. And you know, we haven't actually tried this. I kind of hesitate to do so, but I guess we could try if it actually works. I guess we call filter options, and so it needs the option to text function. And I guess we're going to filter the names. So that's going to be the second argument. We're going to filter over the names. And we have the filter, which is going to be, okay, I'm just using an as the filter. And So this is a list of texts or list of texts. So I don't really need something to transform an option into text. What I'm going to do is I'm going to do to lowercase it, just so the string matches in lowercase. Oh, it's not called that. It's called names. So as you can see, it works. It sort of among these names, it matches, even though it's not actually matching. It does a lowercase transformation of each element and matches the string towards it and returns a sorted list of the original names in the order that they had the best score. So Anne scores higher than Joanne and Suzanne, and the worst match is Lorianne at the end. So this is kind of like just to sort of demonstrate how you would think about these kind of problems if you're working in a functional programming language. You would break things down into small components or small functions that you can use, and you can test them like this in the REPL. And it's sort of, you start to think in these terms after a while. It doesn't come automatically. You start to think like this after using it for a bit. But what it tends to do is after you've done this for a bit, that sort of thinking tends to influence how you write code in non-functional programming languages as well. Because you start to think in terms of transformations and how you can express something as a sort of discrete transformation step. And I've found that it really makes code simpler in a lot of ways once you start doing that. So even if you're not going to be using a functional programming language as sort of in your day-to-day work, I find it's valuable to just sort of try it out a little bit and see if it sort of influences your thinking in day-to-day tasks. We're running a little bit over time, so I thought we'll maybe have time for a little bit of questions, but otherwise this is probably going to be like where we stop today. Thank you. And the final session is going to be talking about what we're going to do is we're going to do a very simple sort of like game loop and render some graphics and have a game that sort of updates or try to implement a simple update over a game state and see how you can express a very simple game like that. And it's not going to be a complete game because we don't have enough time to do that, but it's going to sort of maybe demonstrate how you could structure that kind of problem. And hopefully then we should be done with this. It's taken a very long time to talk about this stuff, but that should be it.